Hello, so today we're going to start a new part 4 on basically it's the beginning of multiple regression. It's the simplest case of multiple regression. Remember, multiple regression is adding another predictor variable, another x variable. And the simplest x variable that we can add is a binary 0-1 variable. For example, male, female. So instead of just having one x predicting a scatter plot in 2D, we actually have, we're going to have another, it will be in 3D, another axis, but it will just have two values, either 0 or 1. I think it's the simplest case to understand, and also it will be easy for us to understand how stratification to control for a confounding variable can also be done by modeling, by adding that whatever you think is the confounder as a covariate, as another variable, another predictor variable in your model. We talked about this so we said in part 2, if you remember, that there were two ways to control for a possible confounding variable in observational data. One was stratifying, and we did that, I think it was on page 20, I'll just check, 21 and 22, let's just remember. We talked about this right here. We said there's two ways to do it. One was stratification, and the next was modeling, which would be we're going to look at in part 4. Well, we're there now, and so what we're going to do is look at the same example that we did, where we saw that there was this negative correlation between the size of one's feet and how many pairs of shoes people owned, and we saw that that this was a bogus correlation, basically. It was just due to the confounding effect of gender. So when we stratified, that goes away. So now let's see how we can get at the same thing by multiple regression, by adding gender as a binary, as a variable, as an x variable. Okay, so that's what we're going to do. So we are on chapter 12 here, the beginning of chapter 12, page 69. Okay, so let's just write that. That's page 21 and 22. So it's actually one of the main uses of multiple regression is to include a likely confounder. And we're going to explore that fully later on. For now, we're just going to look at the very simplest case of doing that, and that's a 0-1 variable. Okay, so we had this data that I just showed you where we said that the bigger one's foot is, you know, the fewer the number of shoes people have. And we saw that gender is a confounder because genders both, when you're a female, you're going to have more, females tend to buy more shoes, so that's going to influence the number of shoes people buy. And it also, females tend to have smaller feet, so it influences the size of the foot, the shoe size. And let's look at this data and see that when we suspect gender was the likely confounder, because causing females to have smaller feet and to have more shoes, we can break the population into two groups by gender. And we saw here's males and here's females. So let's look at it in our data program here. And I can show it to you. So this is the same plot is our actual data from a previous Stat 100 survey. And so we can just go to scatter plots, and we'll choose on the X the shoe size, and here's the shoe number, and here's the regression line in the equation that we got, and we get this fairly, this is a very significant correlation coefficient. So it's not just due to the luck of the draw. And this is held up pretty much every semester that we've done it. And so if we want to stratify, if we want to split, you can see that this negative correlation is pretty much going to disappear when we split the plot into males and females. And then if you want to combine the plot back together, you can see what's happening. We have this group, we have quite a few females coded in purple, and they tend to have, as you can see, smaller feet and more shoes. And here's the males coded in yellow with bigger feet and fewer shoes. You can look at these statistics here. The average size of the male has a bigger foot, 10.64 as opposed to almost 8, 7.984. And also the average number of pairs of shoes is about 7 versus about 20 for females. And that's what's driving this. So that is the idea here. And you can remember this, an extreme version picture of this to help you remember would look like this. What's going on, just so you can remember it better, the extreme version would be what? Okay, so we have shoe size here, and we have shoe numbers, number of pairs of shoes, how many pairs of shoes, shoe number here. And the idea is this: we have two groups of people. The females, I'm going to do a very exaggerated version here, where they have a lot of shoes up here, there's a group, and smaller feet, and the males down here with bigger feet and fewer shoes. And so you get this overall negative correlation, even though within each group, here's the females and here's the males, within each group it doesn't look like there's any. It just looks pretty random. Pretty flat there and pretty flat there. So when you split them apart, these are both flat. And here's, you can see that the average for females is about 20 and the average for males is about 7 for the number of shoes. And that you can also see that, look at the males, there are some guys that have a size 15. And the girls are centered more around 8, the guys are centered more around 10. All right. So that's the idea, and you can see the stratification gives us a really good picture of what's going on. So why would we ever want to do anything else? Why even do modeling? Well, one reason, as we talked about, is because we might want to add other variables. And each time we, would add, if we want to do more stratification, we're going to get smaller and smaller numbers of subjects in each group. And you have to have a very big data set to continually stratify. And also you want to, it's simpler to make predictions. You want to make a model that includes a lot of variables in it so you can make predictions with just one equation. It's very nice to do that rather than to stratify into all different groups. I mean, what I want you to understand is exactly how that works. How adding, this is what we're going to talk about today, how adding a variable matches up with stratifying. Okay? That's what we're going to look at. And we're first, so let's turn the page here. That's what we're going to do right here. Let's just highlight it. We're going to look at how adding gender as an independent variable along with the shoe size, that will be a predictor variable, would also work to separate out the effects. How does it do that? Okay? It doesn't, I'll tell you right now, it doesn't do quite as good a job as stratification unless you add something called an interaction term, which we're going to look at in Chapter 13 today. But first, we're just going to add gender and see what it does. Okay? But before we do, I want you to look on this page. What does it even mean? Let's look carefully at how to even interpret the slope of, like here, of a binary predictor variable. So let's just look at what a binary predictor variable does before we even start. By drawing a scatter plot, that's what I've done here, where we just have these two values. We just have, on the x-axis, I just have your either male coded as 0 or female coded as 1. I just want to first make sure you understand what it looks like, because most people say, oh, if you just have a binary variable, you can't draw a scatter plot. Well, you can. Of course you can. I just did it, and it makes sense. So here is a 0, and here is a 1. And you just have everybody, all the males are right here. This is the shoe number. So if you're a male, the best, and here's the regression line between connecting these points. What is it doing? It's a regression line through the average of each of these. That's what a regression line would do here. And so the average shoe size for males is 6.884, and the average for females is 19.74. And our regression equation right here, you can see it down here, is this, where x is the gender variable. It's gender. So that's equal to gender. And so for x is equal to 0 for males, just carries two values, and x is equal to 1 for females. All right, so that's just, we could have written as g, but the program just always does y and x. All right, so we're just predicting the number of shoes, y is the number of shoes, depending on your gender. And it's just, what's this going to do? How should we interpret this? Well, this only has two values. So what does the regression equation give for males? Well, the predicted number of shoes for males is 6.884. Let's just plug in 4 plus 12.86 times what? What's x for males? 0. So it just gives the average for males. That's all it's doing. What does the regression equation give for females? Let's check it out. So this just gives us the average, y bar, for the males. And what do you think it does for females? We have the 6.844, the average of males, plus 12.86 times what is x when for females? X is what? 1. So we add these together, and what do you think we get? 19.74. Okay? Which is the average for females. So this right here, the slope right here, is just the difference between males and females. That's all this is. So this is just the average. Basically, this equation is what? The average for males plus the difference between the average for males and the average for females. The average for females minus the average for males times x. That's what the slope is. It's very easy to interpret. A slope is rise over run. When you go over one unit from 0 to 1, 0 to 1, in the x direction, this rise here, this distance, is our slope. And that rise from here to here is 12.86. 6.84 plus 12.86 is 19.74. So that's all this is. Now, what do you think if we coded females equal to 0 and males equal to 1? What would the regression be? What do you think it would be then? What would the picture look like if we did that? You could just draw a quick picture of it. Just think about it. What would we have? Okay, we still just have, this is a weird graph, so don't get confused. You see how the vertex here, and this is how all our program is, isn't exactly at 0 here. At 0, it's just so we can draw things better. That's all. So if I drew the picture, so I'd have 0 here. Sorry about that. It should go on soon, I think. Sorry, my hand sometimes hits these buttons down there. All right, so we have 0 for, now we're going to have females be 0, right? So females are going to be x equals 0, and then we'll have males, right, have x equal 1 right there. That's what we're going to do. So now the females are going to be, their average is going to be up here at 19.74, and the male average is going to be down here at 6.884, and the regression line is going to go through those two averages like that. It's going to be just the opposite. It's going to be everything's the same, except it's just going to be, the slope's going to be, instead of going, as you go over 1, instead of going up 12.86, as you go over 1, we're going to go down 12.86. So what's the equation? We can get that quite simply. It's what? We're going to have something, an intercept, plus something times x. But when x is 0, that intercept is going to be the average for females. And then it's going to be minus 12.86 times x. Does that make sense? So it would be what? It would be y bar for females minus just the difference between what? Plus the difference when x is equal to 1, we want the male average minus the female average, right? When we have x equal to 1 for males, we want to get the male average. So it's just males minus females. It's not very hard. Does that make sense? Males minus females is negative 12.86. All right, that's pretty simple. I just wanted to make sure you understand what it even means when you have a binary variable on the x, when we add one of those variables, what we're doing there. All right, so now what do we have? Now we have these two, we're going to be doing a lot more of this later on, adding simple regression equations together for multiple regression, but I just want you to get this picture of it first. So now we have these two simple regression equations, both predicting the same thing, both predicting shoe number, but one's doing it from gender, and the other one's doing it from shoe size. Okay? Shoe size. So these are two different x's. And now what we want to do is combine them into one multiple regression that includes both variables. So that's what we're going to do. And that allows us to separate out the effects of each one of them. So the multiple regression equation is going to look like this. All right, gender we'll say is this one. We'll have a slope for that. That's our binary one. And then our shoe size will be x2. We're adding that, okay? And the idea is, another use of the word control, the slope of each predictor in the model controls for the other variable. So what does the slope for gender do? It estimates the difference gender makes in how many pairs of shoes people have for those with the same shoe size. So it's comparing, like I wear a size 10, you take, so me and women who wear size 10 compared to males who wear a size 10. What difference does being a female have? Controlling for the same shoe size. And similarly, the slope for shoe size does what? It estimates how much an increase in shoe size affects the predicted number of shoes for those of the same gender. So this slope's pretty much going to disappear because we said shoe size doesn't make that much difference, right? Doesn't make it that much difference at all. So this slope that we had that was quite large, of negative 2.154, once we control for gender, once we say, look, you're comparing people of the same gender, look at the females. Look at the females. It's this idea. Just looking at the females, how much does shoe size make a difference? And just looking at the males, how much does shoe size make a difference? And it's negligible. There's a tiny little effect. So we should see a tiny little slope that's probably not going to be significant. And sure enough, when we do this, here's the multiple regression output, that's what we're going to get. We are going to get, here, let's just look at what the output looks like, and we'll do it on the program in a minute. But now we have to do analysis of variance because we have two slopes. So this is analysis of variance for multiple regression, and we're going to include an x1 and an x2. So our x1 is gender right here, and there's the slope for gender, and our x2 was shoe size. And these slopes right here, these are our parameter estimates. Here's our equation looks like this. That's what the equation looks like. It has an intercept given by that right there. That's our intercept, B0. And that's the standard error for it. That's the z statistic, and that's the p-value. I'm just looking at the output here. Then we also have a slope for gender. Right here, that's B1. So this is B0. This is B1 times X1, and this is B2 times X2. And this is Y. So that's our multiple regression equation right there. All right, and then we have some errors here too. Plus error. Okay, and this one's B2. So now how many parameters do we have? The number of parameters is equal to, what do you think? Anybody, how many parameters do you think we have here? 3 parameters. 3 parameters. Look at this. This output on this program says number of x's. Why is it 2? Because it's 2 x's, even though there's 3 parameters, right? It's p minus 1. The number of x's is p minus 1. Does that make sense? All right, so p is 3 because we have 3 parameters that we're estimating. Let's see what else is on this output. We have n here. So this is our sample size. There were 1,046. 1,046. Now, can you see how these degrees of freedom make sense now? Let's zoom in a little more so you understand the output here, because we've done this with simple regression, but we haven't done it with multiple regression. Multiple regression, we just have the 3 parameters now. So now look how our degrees of freedom here change. This is still n minus 1. N is 1046, you see? So that's n minus 1, the total. Now remember, what this regression is the same thing as our model. Our model is a regression plane, actually, but it's a regression model. So sometimes people say sum of squares R instead of sum of squares model. So you'll see it both ways. So this is the same thing as our model. And of course, this is our error. And that's our sum of squares. These are the sum of squares for the model, the error, and the total. All right, and so this 2 comes from where? Remember, it's p minus 1, and p is 3. So that still works. That's p minus 1. And how about this? This is n minus p. Is that right? Is that right? Is it n is 1046. Is it minus 3? Yeah. And it all adds up. So it's what we've already done, but now we just have another parameter added. So it's doing it's doing the same thing. And now, what else do we need to understand here? Why don't we look at it, because you'll be doing it for your homework too. Let's look at it on the data program. So let's look at this. So now if you want to, so let me just show you something. All right, when we do these stratification, we get these two separate plots. Notice that the slopes, even though they both look super flat, and they're not exactly the same, right? They're not exactly the same. Here's one slope, and here's the other one. So the female looks slightly bigger. You can see this when you combine them. The blue line is slightly bigger. Now, when you add gender as an independent variable in a multiple regression, what it does is it forces those two slopes to be the same. So it is going to give us these equations, right? And if you look at your printout, do you see how it just gives you one slope for the shoe size, 0.2472? When really, they're not, those aren't the real slopes. If you really wanted to fully stratify and get all the information, you would have to add another term that would be a multiplicative term, an interaction term, and that's what we're going to do later in the hour. But in this case, people wouldn't do it because these slopes are pretty much the same. So it's not worth it. They just wouldn't bother, and we'd just get our multiple regression equation would lose a bit of information because it's going to give us the same exact slope. All right, so now if we went to, how are we going to get this? If we go to regression, we're going to choose our y variable as the number of shoes. And if we just chose our x variable as gender, we get the same equation we did before. The intercept is 6.884, and the slope for gender is 12.86. I just want to show you that. If we just did shoe size, what would we get? We'd get, we should get exactly the equation you see at the top of page 71. It has quite a big negative slope for shoe size, negative 2.154. That's deceptive. That's due to the confounding. But now we're going to put both of them in together, and it gives us the printout that you see. You see that this shoe size slope is no longer significant. It's no longer significant. It was just due to the confounding effect of gender. Gender is super significant. Now we could analyze this as a chi-square and a z, or an f and a t. And it's nice to look at the difference. You could anticipate what will happen. The model's going to be exactly the same. It's just the statistic that's going to change. The model will be exactly the same. You'll get the same intercept and slopes. You'll get the same R. Everything will be the same, except our t statistic, as you know, is going to be a little bit smaller for each one of these, just a bit smaller than it was. The t stat will be. And the p-value will be a little bit slightly bigger. Hardly, you can compare this to what you have in your notes. compare that. That's what we've talked about a lot before. The t, not the critical value of t, but the t statistic, because it's, is going to be a little bit smaller. It's computed with the, the formula for it. You're multiplying by a factor of square root of n minus 2 instead of, or n minus 3, whatever. It's going to be a little bit smaller. It has more error. Okay, so that's the idea. Any questions so far? And now you can show this ANOVA table down here, and that's what we see. But whether you use a z or a t is not going to affect any of the parameters here. We're estimating them, they're exactly the same. And the r is going to be the same, the r squared. It's just the p-values will be slightly bigger with the t, which is why people like the t. Any questions on that? All right, so now, let's see, what should we do now? Why don't we go back to any questions so far? All right, so let's just go back to our document camera and say, all right, so now we have this multiple regression equation right here. And let's just make sure let's see what it simplifies to. Okay, what does it simplify to for males and for females? So males are easier to do, so let's do them first, just simply because we arbitrarily coded them as 0. So x1 is 0. x1 is our gender right here. Okay, for males. So now, what is that going to simplify to? So we can do it. We'll have 4.255 plus 13.51 times 0, that's x1, gender is 0, plus 0.2472 times the shoe size, x2. All right, and so for females, what do we have? Females are 1. So you can see it's going to give us so multiple regression forces both of them to have the same slope, even though they don't exactly have the same slope, but they're close to it. The same slope, and just different intercepts. This intercept for females is much bigger. It's 17.765. Okay? As opposed, this isn't exactly the average for males and females because you'd have to add this on. If you added on the average shoe size for each, you would get the average. Okay. These are exactly the same equations we get when we choose equal slopes. Exactly the same equations we get when we choose equal slopes. Yeah?
So for the female one, you said x2 equals 1. So then why did you plug the 1 into x1?
Oh, x1 equals, yes, sorry. Thank you. Who else caught that? Thank you. I really appreciate it when you do that. It helps a lot of people. Really, it's confusing to have any of the notes. No matter how small you think it is and you understand it, everyone, including, especially me, appreciates getting it correct here, okay? So please, no matter how minor, stop and tell us. So, because, we want to be clear. Anything else? Thank you. All right. So now, let's move on. And now we're going to look at interactions, how adding an interaction. All right, let's just look at the summary here first. So multiple regression makes predictions for y based on more than one x variable. Now, if different x's are correlated, the coefficients in the multiple regression are not the same. What do I mean by that? x1 and x2 are correlated. x1 is gender and x2 is shoe size. So look what happened. This, if they were uncorrelated, we could just put these, we could just combine these equations. We could have the same coefficients here. They wouldn't change. But look, this negative 2.154 almost turns to 0 in the multiple. It becomes very small. That's because these two are correlated. They change because they're looking at the effect controlling for the other one. All right, so that's very important. Under some circumstances like this one, multiple regression can be used to separate the causal effect of one x on y from the confounding due to the other x's. We can do that because gender happens first and it's a random assignment. And this multiple regression forces the same slope, all right? Next chapter talks about how we can change that, what we have to do to change that. And then a binary variable in a regression model is typically expressed as a 0, 1 variable. Okay? You don't have to. You could express it as 1, 2, anything you want, but usually it's expressed as 0, 1. And it's arbitrary which one you assign 0, which one you assign 1. You could reverse it. All right. Now, so now, you know what, I think it's a good time to make sure your homework is on chapter 12 is going in the opposite direction, going from having two separate male and females equations to combining it into the stratified equations and combining it into a multiple regression equation. The homework is posted now. It's really nice homework. It's going to give you a visual display of what's going on too. But I think we should do some examples of that to help you before we move on. So get out your iClickers while I pull up the homework. Not the homework, but all right, so this is, here are two, let's say the two simple regressions had exactly the same slope, 0.1. All right, and now we want to combine these two separate, this is the equation for males and this is some equation for females. And they have different intercepts. I want you to fill in the blanks to make a multiple regression equation that includes, you know, gender, 0 for males and 1 for females, this gender variable that gives you exactly the same information as these two. Now, this one's easy. The slope for x must be what? Does the slope depend on gender? No, they have the same slope. So what do you just choose one of these? It's not, it's this, let's say they had the same exact slope. All right, so can I stop it? Did everybody get a chance to answer one of these? Okay, I'll stop it in I'll stop it in 5 seconds. Just choose one of these. All right. All right, so the answer is E, and everybody pretty much got that. Great. All right, now, because they have the same slope. In chapter 13, where we're headed, they're going to have different slopes. All right, so now let's look at our next question. We'll start this one. Fill in the blanks to give the same, okay, so what must the intercept be? This is the blank I want you to fill in. And a big hint is do it first for when males are when G is 0. So do that first. Fit it to the male equation. That's what you want. Always start with the simplest one. When G is 0, what do you want to get? What do you want that intercept to be? Okay? Does everybody understand? Okay. And just a few more. I'll just give you a minute to finish this. Okay. We'll stop it. And the answer is 7. All right. Why? Well, let's go. All right, because when you just eliminate that G, when G is 0, you want to match up with this equation. Now, when G is 1, you're going to want to match up to that equation. So let's look at our next question. Here, fill in the blanks to give the same information as these two. Remember, when G is 0, you already got, when G is 0, don't you match it right now? When you eliminate that G, when G is 0, it's perfect for males. We just want to make it perfect for females when G is 1. So what must that slope for G be? We want to match it up to this. When G is 1, we want it to give the female equation. So what must it be? All right. Okay, I'm going to stop it in 2 seconds. Everybody vote. All right, the answer is 13, and that's good. Most people got 13 because you just want, look, G only takes on 2 values. When G is 0, you don't have this drops out and it matches up with the male. When G is 1, 7 plus 13 is 20. So the G is only, if the slopes are the same, that variable is only affecting the intercept. That's all it's doing. It's saying when they have the same slopes, it's only affecting that intercept. Does that make sense to everybody? All right. Now, let's see what happens when they have different slopes. So let's go to the document camera, and this is chapter 13. Yes? Do you want me to go back to that? Okay. Whoops. 3 parts. There's the inner, yeah, sorry, this is screwing up. It's probably simplest to look at it right here, right? Or right here. Do you understand your question? Okay, the question is, why are there 3 parts? Is that what you're asking? Yeah. Okay, when there's only 2 parts here. Is that what you're saying? Yes. The simple equations both have 2 parts. But if we want to combine them into one multiple equation, just one equation, we have 2 equations, 2 simple equations. We want to combine them into one equation that is that can stratify back into these 2 equations. So that means we have to include a variable for gender. Does that make sense? Yeah. Okay. That's the way we're going to stratify into those 2 separate equations. All right. Thanks for asking that. And let's go back to the document camera. All right. Okay. So now, as I said, multiple regression forces the same slope for all levels of each variable. They all have parallel slopes. So that was appropriate in the last example because both the male and the female slopes were about the same. They weren't exactly. But what if the slopes aren't the same? What if the relationship between shoe size and shoe numbers differs for males and females? So here's a different survey where we can look at this if you want to look at it. It's a different survey, and we'll have to choose a different. It's the fall 2012. Thank you, right here. All right, so let's try this one. So we're going to do the same thing, scatter plot, and here we have again the shoe size predicting the shoe number, and our regression equation's even stronger. This is it. All right, it's almost negative 0.4 correlation. Now let's split the plots to males and females, and can you see, maybe when I combine them you'll be able to see more easily, that they don't have the same. Before I did the show equal slopes, do you see how the male slope is pretty flat, but the female slope is still it's smaller. It's not as big as when you combine them, but it is significant, and so we want to show that. So this means that if we want to get both different intercepts and different slopes, we're going to have to include what's called an interaction term. All right? So let's go back to the document camera and talk about that. All right. The data set is different from the last one. The slopes are different for males and females. See, right here it has a much bigger negative slope, stronger negative slope for females. It appears that foot size doesn't have much effect at all. Look at that. That slope is, boy, I'm sorry, this is very difficult to see if you didn't have that in front of you. It's just not clear. Thank goodness you have it in front of you. But what I'm talking about is these two different. This is almost 0 for males. You can see it's flat, whereas this is a slight negative slope. That's all I'm trying to show. All right. I call it the Cinderella effect, maybe, because the story is about how beautiful small feet are and how ugly big feet are back in the day. So maybe if that was the way it was when it was that way when I was growing up, I had big feet, and boy, did I dread going to a shoe store. My girlfriends all had lots of pairs of shoes. I had black only. I didn't want people noticing my feet. I didn't enjoy that at all. Thank goodness it's changed now. But I just had one pair of shoes, dress shoes, and everybody else, they had so many pretty glass type slippers. All right, so that might be a leftover Cinderella effect. But so when the effect of one variable, shoe size, on shoe numbers differs depending on the value of another variable, gender, we say there's an interaction effect. That's the term. And we need to add an interaction term to the multiple regression model that allows for non-parallel slopes. So let's do that. So this was the males, and this is the females. Right? So, what do we do? All right, so we have our usual, here's our intercept. And here, right here, was our gender. Slope, that's for gender, x1. And then we have x2, and that will still be for shoe size. But now, we have this multiplicative interaction effect that's, notice it's x1 times x2. So the slope, these two are going to get added together, these two, to form one slope. When x1 is 1, you can change the slope. When x1 is 0, you could just have that slope. All right. Yeah. This says B1, X1. This one? B1, 2. That's what you call it, because it's for X1, X2. It's an interaction. It's a slope for the interaction term. This right here, thank you for pointing that out. This right here is the interaction term. And an interaction term is a multiplicative term. It's x1 times x2. That's what that is. It's a multiplicative term. And it allows your slopes to change depending on the various values of the other variable. You can have a three-way interaction term. You could have x1 times x2 times x3. If I had x1, x2, and x3, then I would have a lot of interaction terms. I'd have the three interaction terms, x1 and x2, x2 and x3, and x1 and x3, and then you'd have all three together. So things get very complicated if you want to include all those interaction terms. But with just two predictor variables, you have one interaction term. Okay? And so y is the predicted number of shoes. Let's just, x1 is gender, 0 for male and 1 for female. Let's keep it straight. And x2 is shoe size. And this last one is gender times shoe size. All right? Now, so here we have these two separate ones, two stratified ones. Okay? These are the two stratified ones. And notice, remember, they had different slopes. This is the Cinderella effect for girls, and it's absent in boys. That's what I'm just calling it, right? So they have two. This is what the data we looked at, and there's two, and we want to change the slope. We want to create a multiple regression equation that gives when x1 is what? When x1 is 0, so when it looks like that, x1 is 0, and we're just left with the intercept in x2, we want it to give that equation. So what should I fill in? When x1 is 0, I want it to give that male. So what should I put in for the intercept here? Shouldn't I just put this right here in here? Right? We want that male, right? This one for males. That should be for males because when we have males right here, we have gender, we have 0 for males, right? So this is 0 and that's 0. So we just have an intercept and a slope, and we want it to match that intercept and slope. Does that make sense to everyone? So that's the best way to start when you do these. Now, we know that works. We know that works for males when x1 is 0. But what about for females? When x1 is 1, what are we going to put in these two blanks? Put in the remaining two blanks. They're not the last two. Remaining two blanks. So what do I put in these two blanks? Well, this one is 0, 1. It has no slope. When for females, this is just going to be a 1. So just think, you're just going to have a 1 in there for females. So I'm going to say, so don't I want it to be this intercept? I want this plus, I want these two together to equal what? When x1 is 1, I want those two together to equal 29.24. Does that make sense? We want these two together to equal 29.24 when x1 is equal to 1. So what should I put in there? 29.24 minus 5.849, right? I want it to be 29.24, so I'll just have to subtract off that. 29.24 minus that, which is 23.39. Together, you want them to add up to that. Does that make sense to everybody? All right. Now, so this is the x1, right? This is x1, and this is x2. I'm just coloring them in. Okay, so now, when x1 is 1, so x1 is 1 here, so this, when x1 is 1, these two together are both going to be the coefficient. This plus this will be the coefficient in front of shoe size. That's x2. All right, so we want this plus that to equal what? We want those two to be negative 1.17 when x1 equals 1. So we just want, what do we want to do? We just want negative 1.17 minus that, which is negative 1.18255. Together they add up to that. They're the coefficient in front of x2. x2 is the shoe size. That's not going to disappear. x1 is just 0 or 1. And when x1 is 0, when x1 is 0, we've got our males, right? When x1 is 1, we just want those two to add up to the intercept there, and these two to add up to the new slope, to that slope. Because when that's 1, we have something times x2 plus something else times x2. Does that make sense? And then it will give exactly the information that we had before. So let's try it as an iClicker and see if you can do it. Let's do it as an iClicker. Just because you have a bunch for homework, we might as well just do some for an iClicker. So let's go and do those. And all right, so let's go to our iClicker question. And this is it. All right, so what I did here is I was thinking of the shoes. I was thinking, okay, so the number of shoes men have about an average of 7 plus let's pretend they had a very small positive slope here, and women have an average of 20, and let's say they had a bigger positive slope for the number of shoes. I just made up some numbers. And I wanted to, let's say that was the two stratified, and I want to fill in the blanks to give the same info. Okay, and gender is 0 for males and 1 for females. So what do you think this intercept has to be? Remember, start with the males. The males, isn't gender going to be 0? These two things are just going to disappear for males. So these two terms for males, you want these two terms to match those two terms. So the intercept must be, right? I'm going to stop it. The intercept must be what? Let's stop it. Okay? And it has to be 7, right? Good. All right, everybody got that. Now let's do the next one. All right. That's 7. That's right. Now let's do the next one. And now we've got the 7 in there. And I want to know what the slope for this x must be, right? Now fit it to males first. So when males, you have these g's, these two parts just disappear, right, for males. So you just want to fit it to the male equation. So which one must be the slope for this right in here? That's the easiest way to do it. I rearranged the terms here to make it easier for you. So these two just go away. So you see this part, do that first for the 0, for the variable that takes on the value of 0, males. All right, you got that? Can I stop it? 2 seconds more, a few seconds more, everybody choose something, okay? We stop it, and it should be E. It should be 0.1. Let's see if you got that. 0.1. Okay, so most people got it, but let's think about it. When these two disappear, we want this is the coefficient in front of x, we want this, 7 plus 0.1x. I switched the order of these. Yeah, Does anybody have a question? All right, so let's go to the next one. All right. So that's the answer, filling the equation for males when G is 0. That's all you need to do. That's the easiest way to do it. Just say, okay, males first, just get rid of that, and then say, this is the equation we want to match. Now we're going to work on when G is 1. All right, so we'll just move to the next one. All right, this one. So the slope for G must be what? When G, now, think about it. G is only going to enter in when for females when it's 1. Females are 1, so what do we want? When this is 1, what do we want that slope to be? We want it to look just like this. There's no G in these. We want it to look just like this. Okay. All right. 5 more seconds. All right, and the answer is going to be 13 because we want it to match up with 20. Let's see if people got that. Great. Okay, now let's go to the next one. So that's 13. So this is what it looks like so far. Now our next one is this. What's the interaction term going to be? All right, so you just think what's going to happen. When this changes it to a 1, what's it going to be? You just use the distributive law and you say 0.1x plus what times x should equal 0.5x. When that turns to 1, you're just going to add that together with that. So which of these should it be? And that will give you this term. All right, just about 3 more seconds. And I'll stop it. And the answer is 0.4. Great, that was your best one yet. Great, and that's your equation. And there's the answer. When G equals 1, then the equation yields the correct female equation. Great. All right, seems like you can do a lot of your homework now because that's pretty much, there's going to be a lot of problems like that. Now let's move on. Let's go back to here to the document camera and just finish up this section. All right. Now, I just want to be clear. Some people get confused here. We can find the okay. Yeah. Oh, yeah. What happened? The same thing again. Damn. Why did that happen? All right. Oh, that. Sorry about that. Thank you. All right. So, just read this. This is important. There's a lot of concepts here. And what we first started off, we said we can find the multiple regression equation by combining the 2 simple stratified regression equations, right? That's what we just did. But don't confuse these stratified regression equations below. Don't confuse what we've just been doing. They're each making predictions using the same x variable. We're just stratifying, right, by gender here. Don't confuse them with something that we're going to be doing a lot, which is combining the simple regression equations, like the ones we saw at the end of chapter 12, each making predictions from different x variables. When we saw the one, you know, these, where you're making them from different x variables, gender and shoe size. That's something we're combining different ones. That's a completely different idea. So I just wanted to make sure you don't confuse those two just because they were presented at the same time. Okay, that's all. All right. In this case, we're just combining the 2, here, what we've been doing and on the homework so far, we're just combining the 2 stratified simple regression equations into a multiple one that gives us exactly the same information, exactly the same information. In the previous case, where when we combined 2 simple regression equations into a multiple regression, one for was gender predicting the number of shoes, and the other was shoe size predicting the number of shoes. That gave us a lot more information. It gave us the effect of each variable after controlling for the other variable. That gave us a whole lot of information that we wouldn't have had otherwise. All right? This is just another way to do stratification, showing you how to go back and forth so you see how the multiple regression equation what it means when you break it down. All right, and so what should we do here? So let's just look at the printout. So now if we wanted to look at this printout, what do we have now? Now we have more parameters, right? How many parameters do you think we have here? We have 1, 2, 3, 4. And let's just make sure the printout agrees with what we got here to make sure we did it right. And it does. Our intercept, this is B naught. It matches up 5.849. The gender slope, 23.39, that matches up. The shoe size slope, this one matches up. That was this one. That was this one. And this is the interaction one. 1, 2. We could call it B3. I don't have to call it B1, 2. We could call it B3 if you want. Just so you see that now you have 4 parameters. So this is 4 parameters. And that's why our degrees of freedom for the model is 3. It's 4 minus 1. And here it works out the way that, but look at this. What is not significant? Again, this is not significant. Only these 2 are significant. They have very small p-values. This is significant and this is significant. Only gender and the interaction term are significant. Shoe size is no longer significant. Shoe size hardly matters once gender and the interaction term are put in the model. So again, shoe size, that was a bogus, deceptive, misleading overall regression that we got. It was due to confounding. So I think that's pretty much it. Let's look at see if there's anything in the summary we need here. So the idea is you have these main effects, and then you have the interaction terms that are the multiplicative effects. I think you understand all this. Let's see. I think you can just read this on your own. The interaction term allows the slope to change. That's the main point. And without an interaction term, the slope is the same. You have parallel slopes. So that's the idea, and I think that's it for today. Have a good weekend. Oh, I want to warn you that your homework's long. So get started on early, and you have to use the data program. So start on that homework early.